Bom, de novo, se no meio da aula, se vocês querem perguntar em português, tudo bem? Eu vou traduzir para inglês, mas vamos começar a aula de hoje. Okay. So, we have already seen this check cohomology. So, we will always talk about smooth projective varieties. And we have already, of course, so far everything over complex numbers, and for me this is just a complex manifold. And we have seen these check cohomologies, and at the end we have also homologies. And the easiest way to introduce the homology with using check cohomology would be say that, okay, let's just work our rational coefficient, and this will be just the dual of the cohomology. But of course, we construct this through simplices and a singular homology. Anyway, so the objective of the next 2-3 talks is to construct algebraic de Rham cohomology, and using hypercohomology. And we'll denote it again by the classical with this notation HM de Rham. So first of all, it is algebraic in the sense that only we will use polynomials. At the end of the day, X is a zero set of polynomials, and then so we constructed this using a polynomial. So there is no C infinity function involved, and that's actually the fun of this de Rham cohomology. In order to say that we are dealing with algebraic de Rham cohomology, we will use this X defined over complex numbers. And since it is defined in algebraic framework, at the end, if X is defined, we can also talk, if X is defined over a field, then we will define this one. This will be any K vector space. And in some situations, we will assume that characteristic of K equal to 0. But anyway, so the idea is that we want to construct this. So so what we need Zarsiki topology of X. Maybe very fast. I remember this one. So for the Zarsiki topology, let's say if you have this open set UI xi not equal to 0. So let's fix the notation. Remember that my notation of coordinates in Pn is x0, x1, xn, and then this is let's say this is an affine chart for Pn, and at the end let's say x ui is a 0 set of polynomials. and let's call this one VI. And okay, so in order to find a topology on a VI, we need to define the topology on UI. So you see that these UIs are isomorphic to, let's say, C to the N. So I will take the notation for variety X over complex numbers, but slowly we will move to algebraic notations. Maybe I remember that this algebraic notation for this is A Cn, and C being the field of complex number that can be replaced by any field or any ring. Anyway, so what is the so we have to define the topology in Cn, closed subset of Cn. They will be just these are just a zero set of polynomials. I'm just making an overview of Zarsiki topology very fast. So the zero sets will correspond to the closed subset, and the open subset of Cn. They will just complement of closed subsets, and then we have the topology for Cn, and then we from this one we have the induced topology with the V for V's the variety. Just a minute. No, hold on. Okay. So we have this we have defined the topology in Cn, and then we define the topology for V. Let's say this V equal to Vi. And yeah, then this will be the Zarsiki topology, but maybe some open sets which are very special for us, affine varieties. And what are these affine varieties? And let's say closed subsets of let's say Cn, the closed subsets of Cn, and so this means that they are zero sets of polynomials. And okay, and something maybe let's mention it, that X, my projective variety, is covered by n plus 1 affine varieties, affine open subsets. And this is just these are Vi. Let's see. Okay. Okay, vi equal to x intersected with this ui, which was xi not equal to 0. And okay. Okay. So so we need the well. This we will need for computations. And maybe what else I can say? Okay. Now, what else we need is the concept of differential forms. Differential forms, algebraic differential forms. And so anyway, we have to we must be able to translate the differential forms of differential geometry to our algebraic context. Maybe from now on, let's try to use algebraic geometric notation. As I said, I will use this notation. If you want to, let's put K, I have arbitrary field. And if you do algebraic geometry, you will see that there is this spectrum of K x1 until xn. You will find this one. But in order to keep our geometric intuition, you can always think of this an just as let's say in our complex context Cn. And remember that at the end, the points of Cn are not important. What is important is the ring of functions of this variety. Anyway, all the computation that we want to do here at the end will reduce to computation over our this ring. And but sometimes sometimes it is convenient to use this notation to keep in mind that we don't use beyond the field K. And yeah, okay. So let's see the difference. So we have to construct differential forms in our context. So let's go to this chapter. Maybe very fast I explain it from my book. Let me see, which one is this? Okay, so let's see. It didn't work. Okay. Okay. Oh no, actually not this one. Not this one. Just a moment. One moment. Okay. In the window. Okay, let's do. Okay. So. We have to get familiar with the concept of differential forms in the purely algebraic framework. Maybe. Well, let me start from a pure That's purely algebraic framework in this way. So if you have two rings, R and R check, at the end I want to make to define the concept, this concept of Kähler differential forms. Maybe for simplicity, if you want, you take, for example, R any ring, and R check, just take this ring with x1, xn plus 1 variables. And this is actually, this is our also main example. So the Kähler differential forms are actually differential one forms that we are going to define. So what is this? It is the free module, the quotient of the R check module freely generated by symbols. So if we first consider the R checked as just new symbols, but we so generated so from this free modules we want some properties to be satisfied. First of all, when the differential of the elements of R I want to be 0, so the elements of R I want that they become constant. So this means that dr must be 0. So that's why I am quotienting the R check module freely generated by symbols dr modulo its submodule. This means the quotient by its submodule generated by this dr. So the differential of the elements of R I want to be constant. And from another point, I want that the Leibniz rule to be valid. So DAB must be ADB plus BDA. So don't confuse D with AB, because D for us will be always the differential. And also the linearity, the DI plus B, that I want to be that it is DA plus DB. And okay, so it turns out that this purely algebraic definition of differential forms is enough for our purpose, and at the end they will give us the concept of differential forms when we consider our varieties as complex manifolds. Anyway, so this is I'm not talking about this section 10.3 of my own book. So you can find also this some part of this exposition in the Hart-Shorn book. Okay, so then it turns out that if our check is a finitely generated R module, then this differential forms. But again, remember that at the end this will be the differential one form for us. But usually in the algebra courses, you don't one doesn't write this to the one. So this let me just so usually they will appear one on top of this omega here. So then there is this differential from R check to this one. It is just taking R to dr. And I think well, I don't want to put too much emphasis on this, because you can also keep your C infinity version of differential forms and go on during the course. Again, the algebraic notation, when R check and R, you take their spectrum, there will be varieties. The spectrum of R is T, the spectrum of R check is L. So there you will want to introduce this more geometric notation. But maybe just for to proceed the course. So differential R-I forms will be defined by the wedge product of the differential one forms. And again, this wedge product is purely symbolic product. And so don't worry about this changing notations here, because I want to just from the ring, pass from the ring to varieties and so on. At the end of the day, as I said, this wedge is again a purely symbolic notation. This means that at the end, omega I is the quotient of the R check module freely generated by the symbol. So these are also symbols for me. But I want that the symbol to satisfy something. Module its submodule. So what is the main property of the wedge product? The main property of the wedge product is that if one of these two guys, let's say consecutive guys, they are equal, then this must be 0 in my module. And it turns out that this is enough. And actually, if any two elements here, here are equal, then this wedge product will be 0. And maybe again another important things that we can introduce this differential from omega I to omega I plus 1. Again, these are maybe you go to this ring notation. Differentials, and the differential is defined in a canonical way that we learn it from differential geometry or in algebraic topology. So dA, dA1, dAi, and A1, AI being in R, they just make dA and then can make a wedge. Okay, so maybe let's so the basic idea of this section is that really I don't need to go to infinity context and to go to tangent spaces, cotangent spaces, and so on in order to define differential forms. And maybe one good exercise is that when, for example, as I said in our main example, when our check is x1, x2, xn plus 1, R being an arbitrary ring. In this case, our differential R forms are just classical way of writing differential form in an affine variety. Coefficients being, let's say, polynomials, and then the xk1, the xk2, the xki. Okay. Let me see. Okay, so I'm going to proceed further with the differential forms. But if you have never seen the concept of differential forms in purely algebraic geometric framework, maybe you have a look and try to do, let's say, some exercises. For example, these exercises here, in order to get familiar with differential forms in algebraic framework. Okay, so let's go back to the notes. Okay. So, and so the moral of the story is that we started from x Pn. We said what is Zarsiki topology. So let's say U. Let's again U affine open subset. And the moral of the story that I can now talk about differential forms. Let's say omega I. Let's use the shift notation, omega I x u. These are differential forms, I forms in in U. And maybe very fast I rewrite this one, like let's say. So just remember that at the end U is a subset of some Cn. So let's say U is the zero of the ideal I, and the I is the zero set, the ideal generated by F1, F2, and the F chi. And okay, and so I have this OX U, the ring of function on let's, for the moment it is let's define it. So the ring of functions of U, it will be just Cx1 Cxn divided by this I, ring of functions. And well, so for the moment, for on my purpose, I will assume that I contains all polynomials such that they are vanishing on U. But in general, I can be any ideals, and this is one of the reasons that at some point maybe we start using the language of a scheme. For example, this I might be non-reduced and so on, but this will produce some complicated issues. But for the moment, just let's skip. Let's do algebraic geometry ala Shafarevich, not ala Grothendieck. Okay, so then omega, let's say U differential I form in a U will be just omega I, and if this is, let's call this, it will be just so the first ring is C X. Maybe what was my notation? Let me. Okay, Cx divided by this I. So this ring divided over C. So this means that, so I want that the complex number to be constant, and that then these functions may not be constant. So then in a similar way that I did in the presentation, then we define these differential forms in a purely algebraic way. Okay. Okay. So the moral of the story is that at the end we have the sheaf of differential I forms, let's say omega I x on X, and also we have this complex. So let's say omega 0. So maybe let's say omega 0 differential omega 1x, omega 2x, all of them are t, omega ix, and go and so on. And let me, okay, so we will have this complex, and again it is it's not so difficult to see that the decomposition of this twice 2 is 0. And let me see. Okay, so far we have algebraic variety X and this complex, and what we are going to do is that using this this complex, we can define the algebraic Teorema cohomology. Okay, so let me Okay, so let's maybe from now on, I will try to explain this one. H M the Rham. So we'll abbreviate this one to let's call this omega bullet X to say that we have a complex. X over C is just hypercohomology of X of, so the hypercohomology, you use this H with extra line. Then, so I'm going to explain what is hypercohomology. And again, if you, I don't know if you have seen, if you have any heard of hypercohomology or not, but the point is that I want to do computation. So at the end, I will introduce the hypercohomology in a more check cohomological way. So, so what is hypercohomology? And so the hypercohomology is like homology, it's like a check cohomology, but instead of sheaf of abelian groups, you have the complex of abelian groups. And this is, and it was invented by, let's say, Grothendieck. But after introducing a hypercohomology, I will explain a little bit more the prehistory of hypercohomology, which goes back to Picard and Atiyah and Hodge. But for the moment, the idea is that I want to define a new cohomology, because using this new cohomology, I will be able to do a kind of Hodge theory, not using harmonic forms, but using let's say algebraic form. Okay, so let's go to the hypercohomology. Actually, I will change the plan of today. I was thinking of talking about Atiyah-Hodge theorem, but let's see what is hypercohomology.
Hossein, so just to understand, so you constructed a sequence of complex of sheaves, right?
Yeah.
And hypercohomology is cohomology with coefficients in a complex of sheaves of abelian groups. Okay.
Perfect. Exactly. So maybe one big well, let's say discovery or of Grothendieck was that at the end, to categorify everything. At the end, when you categorify things, the category of abelian sheaves, then you can consider the category of complex of abelian sheaves, where the complex of abelian sheaves are the object. So at the end, the cohomology is the same as the hypercohomology. But I don't want to use this kind of unification of the cohomology and hypercohomology using this derived category and so on. I want to really do computations. And at the end, when you see the literature, you see a lot of abstract language with not so much computation. And for this reason, I want to keep, let's say, I want to say that this hypercohomology it always is attached to a complex of abelian sheaves. Okay, so let's go to this. So this is my main example, but in the text I will okay, so let's go to section 3.2 of my book with my former student Villaflor, which we must polish the book, but we are kind of lazy to do so. Okay, a window. Okay. I choose the wrong page. Oh, sorry. I choose the wrong window to share. A window. Okay. Okay, so first of all, the concept of the hypercohomology is attached to any complex of abelian shifts on a variety, and on a topological space. So it is again a purely topological concept, and we will use it in our main example that I already explained you. So we just need this sheaf of abelian groups, S0, S1, the concept of differential. So from the concept of differential, what we need is just a D composed with D equal to 0. This will be, that's actually is needed in the definition of a complex of sheaves. So even so that I'm going to write define the hypercohomology in this general context, maybe you just keep in mind our main example. Okay, so I will need a covering. So again, like check homology, I need a covering, and all the computation will be done in a covering, and that's why it will be also a kind of combinatorial object attached to a topological space. Okay, so the covering, so maybe let's mention this two covering that I need. So for a smooth projective variety dimension n, for simplicity, let's take our complex numbers that you can do our arbitrary field by yourself if you really need it. So okay. So first of all, there is a covering of X with n plus 1 open subset. And this is a kind of, we will need it at some point. Let me explain. So remember that when X is a subset of a P n, I did it. It has all Pn has already a covering with n plus 1 open sets, and this affine open set, and this n plus 1 affine open set will give a covering of X. But one thing is that this is too much open sets. We can reduce the number of open sets to n plus 1, where n is the dimension of the X, but whereas this capital N is the dimension of the projective space. And actually, the proof is very, very, very simple. And what is the proof? So the covering is going to be kind of given by GI not equal to 0. What is GI? GIs are linear equations in the coordinate, and so GIs are degree 1 polynomials, and GI equal to 0 will give me this Pn capital minus n minus 1. So we have n plus 1 equations. So the zeros of n plus 1 equations of degree 1 homogeneous polynomial will give me a P. They will give me this this maybe. Okay. So this means that at the end, okay. So we can take a linear subspace of Pn given by G0, Gn plus 1, such that this doesn't intersect X. And in a moment, I will explain why this happens. If you take this linear space, then since this linear space doesn't intersect X, you can immediately see that Ui equal to 0. Of course, is restricted to X. They form a covering of X. Maybe. Okay, no. So the point is that actually I have to write this is a kind of this intersected with X. So Ui is equal to Gi not equal to 0 intersected with X. Okay, and well. And well, it's a kind of easy exercise in algebraic geometry. Once you have a variety of dimension n, then always there are these linear projective subvarieties of Pn which do not intersect this one. And for instance, maybe let's say one proof would be that, for example, what is the degree of x? For the definition of degree of S, one intersects P capital N minus N with x, one get degree x points. And if you reduce the dimension of this projective space by 1, for example, if you take this guy inside this one such that it doesn't cross this degree x points, then you will get the desired projective space. Anyway, this is a very easy exercise in algebraic geometry. So for projective variety, we can take n plus 1 open subset. And maybe another covering that we will need for our purpose is this smooth hypersurface X of degree D. This is the Jacobian covering, and the Jacobian covering is by UI such that derivative of f are not 0. And actually, since f is smooth, this means that all these derivatives equal to 0. And f equal to 0, they do not have common zeros. So it will the fact that f is smooth, the x is smooth, will give me the fact that this is a covering of x. So this is again this in kind of basic fact in algebraic geometry. Anyway. So these are the coverings of the projective variety that we will take. So let's, in order to do hypercohomology, I will need this diagram. Let me explain this. What is this diagram here? And maybe I do it in the paper. Okay, let me proceed writing such that. Okay, let's. Okay. So remember that I had the. Well, I take a complex of abelian sheaves. I mean, what's it? Sn. Okay, and also remember this notation. Okay, so S. Okay. SI G. I have my covering. I have my sheaf SI, and remember that we define the group of cochains symmetric. This S was standing for symmetric, and at the end G cochains. And so let me again remember what was let's say here. What is this element here? So remember that I take omega I. So first of all, there will be G plus 1 intersection of open set, and there is this I notation also. In order to simplify my my notation, and maybe to make it easier to remember it, for example, when I will put for element here on top, I will put I. so that it is clear that this is element in Si, the sheaf Si. And from another side, then this is something defined in G+1 element. So omega I, it consists of omega I, and then G0, G1, G. Actually, not. I have to. I0, I1, I2, IG. So where this is the section of Si in UI0 intersected with UI1 and then UIJ. So at the end of the elements here, it contains a lot of elements in G+1 intersections of my covering. Okay, so this we had defined, and remember that we defined how we define the check cohomology. Maybe I remember the check cohomology. Okay, so how we define check cohomology? We define in this way. So S I J. So this I is fixed. I am not mentioning G+1. Maybe, yeah, exactly. Now I am writing from bottom to top. In a minute you will see why. Si G-1, then these are delta, delta. So the check cohomology will be maybe check cohomology. It was just a kernel delta divided by image delta. Okay, so this was our check cohomology. But then now the point is that we have more shifts. So the point is that, for example, I have Si+1 also, Si+1, and in the same way, I can form the check cohomology complex of Si+1. And also I have, let's say, Si-1, D+1, G, D-1, delta, delta, delta. And in each column, I get, doing a kernel delta divided by image delta, I get check cohomology. But from another side, we started for our SIs comes from complex. So this means that we have also these D maps. And we know, so the hypercohomology is a kind of making a mixture of these two. So remember that then delta is equal to 0, D composed with D is equal to 0 also. So basic idea of the hypercohomology is to define a cohomology using both. And let me explain the idea. So the point is that we will make direct sum of these anti-diagonal abelian groups. So let's say okay. So I will define, let's say, this L. In this case, L I plus G. In this case, it is. Oh, sorry, this is just one. There some must be M. I have made a mistake here. Here is g minus 1, g plus 1. Yeah, okay. So let me explain this. So there will be li plus g minus 1. So what I'm saying, I have here abelian groups. I will take this anti-diagonal abelian groups, and I will define this guy as a direct sum of all these abelian groups here. So at the end of the day, what is the definition? Lm by definition is direct sum equal to 0 m s I m minus I. And and it turns out that okay, so well, let's think. I have a double complex, and I want to produce a simple complex. So and then I want to kind of so let's say differential from here to going to here. So I have to define this differential from t from Lm going to Lm plus 1. And let's do also this one. Okay. Okay, so maybe again I write it here. So Lm was direct sum equal to 0 until m s I m minus I. I want to define d from Lm to Lm, and at the end I want that this dd to become to 0, decompose with d. So the definition is that d, let's say d, let's say element here, omega. Maybe I first write it in Sig, will be delta omega plus minus 1 to the g d. In a moment I will explain this one. So again, from where it comes, this definition, I think it will be natural once we also verify this one. Maybe I start explaining it in the diagram. Okay, let's go back to the. So okay, so let's return back to this one. So I am here. I want to define a map from here to here, and then from D to here to here. At the end, I want that this decomposed, let's say, this decomposed with this D equal to 0. So I have to say what is the what is the D here. So D of omega here, it will have element here, let's say, by delta omega. And when you go here, what we will have, you will have a d omega. So this is here, this is here. Again, by reasons that will be clear in the proof of this one, we multiply this one with minus 1 to the j being the index of check cohomology. And so omega goes to this one and this one. You remember that at the end, Lm plus, if this is m plus 1, and if this is m, at the end, Lm plus 1 is the direct sum of all these abelian groups. So each piece here will produce 2 pieces in the image. And then, yeah, I will repeat it in all the entries as here. And again, why this sign appears and so on, I think it's a kind of trying to define a reasonable differential operator such that this d equal to t is satisfied. So this is, again, I will put this one as a kind of exercise. So if you do twice this one, then you see that each element will produce 4 elements. If you from here, you go to here, there are 2 elements. But if you apply D again, there will be 2 elements coming from here, and another 2 elements here and here. And there will be cancellation, and at the end, the decomposition with D will be 0. Okay, this is so what we reach. At the end, we reach to this complex L1 D Lm D D and so on. And again, exercise decomposed with D equal to 0. And yeah, then we started from covering. So the hypercohomology of this complex S-bullet is just what? It is the cohomology kernel, let's say kernel, this Lm going to Lm plus 1D divided by image Lm minus 1 D Lm. And okay, and maybe I just very fast remember this one. Again, there is one idea of to get rid of the covering. The idea is that I want to put here X and not the covering. So we have to go to this direct limit. Maybe I show this direct limit in the book, and we finish. Okay. Okay, so we define the, let's hypercohomology relative to a covering in this way. And well, again, like in the case of classical check cohomology, we have when one covering is the refinement of another covering, we will have maps, and these and let me see. Again, there was this how these maps are defined. It has to do with this homotopy argument, purely algebraic homotopy argument. But anyway, and then the point is that if we define the hypercohomology of X with coefficient in this complex S-bullet, then it will be just a direct limit, and this is the definition that we have. Okay, once again, this definition is useless because at the end we don't want, with this taking direct limit is a kind of very boring way of defining something. So we want to reduce our computing the hypercohomology to a covering, just fixing a covering. And in order to be able to do this one, we have to use this theorem. I will just announce it. Okay, if the covering is acyclic with respect to all abelian shifts, remember that what it means acyclic. This means that the cohomologies of all the intersections with coefficient in SI are 0. And next lecture we will discuss how to find acyclic shifts for our main examples. And once we have this acyclic shift, it's a kind of exercise in topology that at the end the hypercohomology is the same as hypercohomology related to this covering. Okay. So maybe let's share 5 more minutes.
Hossein, just a question. Can
Okay.
you explain again what is a cyclic?
Okay. Maybe I write in the paper. Okay. Okay. So the point is that at the end I want to replace instead of ux. I defined by no, actually I defined this by direct limit, and I want to get rid of this direct limit and use a fixed covering, and say that then this is isomorphic to this one, and this is valid for u, a cyclic for all SIs. And what is this? This means that H, K, all the intersections, UI0, UI1, UIG, with coefficient in this sheaf SI. Let me see. These are all 0 for I equal to 0 for all sheaves, and the old intersection, G equal to 0, 1, 2. So if the cohomology of all the intersection open sets of my covering with coefficient in SI is 0, then I have a cyclic covering for all of SIs, and this isomorphism will be only valid in this case. So this means the moral of the story is that, okay, so remember that what was my main example? My main example was the sheaf of differential forms, and let's say U0, U1, UK, U actually N being dimension of X, affine open sets UI. So let's say I told that I can take covering with n+1 open sets, and so in the next lecture what we are going to do is that actually when we take affine covering, these are acyclic for the sheaf of differential forms, and so in order to compute the check homology, what we need to take this covering with affine open set. And the point is that this affineness will be important. It cannot be any arbitrary Zarsiki open set. It must be affine. And so today I just told the definition of hypercohomology, and at the end again remember that at the end HM the Rham X will be by definition the hypercohomology of M has hypercohomology of X, the complex sheaf of the sheaf of differential forms. And yeah, okay. Any question?
So what you are saying is that if you consider an affine covering for our variety, it will be a cyclic with respect to the differential forms sheaf.
Yeah, I will explain. This is the Serge theorem. It will follow from Serge theorem. That then I will explain it next. next lecture. For the moment, in the general context, I have to take covering such that the intersections, they do not have any non-trivial cohomologies. Let's say here I have also.
Yeah, I mean, it makes sense if you think about like usual differential forms, because like locally you are on Rn in some sense, right?
Yeah, but the point that I will take affine sets, affine. Affine. Okay, if these UIs are small open sets in let's say in Cn, okay, then I have this Poincare lemma and so on. But remember that these U0s are affine sets and they are big. And the fact that there is no, and the and actually the two intersection of two affine sets will be also affine also. And the fact that affine sets, and for any affine set and the coherent sheaf, in our case, the sheaf of differential forms, the cohomologies are zero. This is the Serre's theorem.
Yeah. Okay. Yeah.
I will explain. Right. I will talk a little bit about this one next next lecture. And well, since after assuming all these theorems that like Serre's theorem and so on, then we have to get we start handling the de Rham cohomology. But I think if you are not familiar, maybe when we start doing computation, you can get more familiar with this kind of concept. Okay.